Speaking for you today is Todd Uston, and he will be taking through a mostly gentle introduction to computer security.
Thank you very much. Yeah, mostly gentle. If you're not a techie, you don't program a lot, I think there's a lot you can take away from this, but I'm going to dive down into some math once, just one time, to look at a really interesting result. So thanks. My name is Todd Uston, and it's a pleasure to be here. And this is the computer security tutorial. 1.83 hours of information on computer system security. So first of all, why is this important to us? Well, in today's world, if you're not considering security when you design your systems, you're really leaving the system fully exposed to attackers. Karen Sandler talked a lot this morning about this pacemaker device that didn't consider security, and people pwned it, as they said. And then many system trends really point towards more exposure. There's just a lot more complexity. 11 million lines of source code. In December, they crossed 11 million lines of source code in Linux. And platform populations are growing. These are two things that make for easy attack vectors. In terms of platform populations, there's 750,000 new Android phones coming online every day. That's a lot of attack vectors. So I think the takeaway from this tutorial is that while protecting your software isn't non-trivial, it's definitely not difficult. And you don't have to fix all the bugs. That's one of the things we're going to learn today. You just got to be better than your competitors. And so the first step of that is understanding security risks and the protections that exist. And then we're also going to look at some open source tools that are really useful at building more secure software. If you have questions, I can take a few questions here and there. Please raise your hand. I'd be glad to address that. So let's start by looking at why the world of security is such an interesting place. My background is in computer architecture, and it's kind of a boring area. Over time, I got more interested in fixing broken things. And when you get interested in fixing broken things, computer security is one place you'll definitely land. And computer security is a really fun area to work in, because it's one of the few research areas that has good guys and bad guys. And they compete with each other and they fight, and it's just a very fun area. And that's really how things work. Let's take a look at the development cycle of a piece of software today. First thing we're going to do is develop our application. Then we're going to release it to our customers, and our customers are going to get hacked by attackers. Now note, I don't call them hackers, I call them attackers. Hackers are people that program very well. Attackers are people that are trying to take over your machine. The press always gets this wrong. So attackers try to hack your customers and take over their resources. We'll talk a little bit about what they do when they hack your machine. Customers get upset. They go back to the vendors that supply them with the software, the developers, and they say, okay, well, we'll fix that. We'll do countermeasures. We'll fix your software. We'll add facilities to find bugs, etc. And the system's safer, and then you go back into this cycle again. So that's the arms race of the security world. We're always trying to improve the level of software safety, and then at the same time, the attackers are coming up with more sophisticated ways to attack our software. And one thing we're going to look at in the tutorial today is we're going to look at a small little version of that arms race over a period of about 10 years. It's pretty impressive, the attackers. They're definitely not dumb. They're very smart people. Okay, so why do attackers attack? Well, first and foremost, they really want to gain control of your machines. And they want to do so in a way that is mostly unnoticeable by you. And that is the formation of botnets. Botnets are collections of machines that have been attacked and secured for the purpose of a variety of things. Botnets send spam email. They get around all the countermeasures for spam. You can't send 1 million emails through your ISP tonight. But if you have 1 million machines and each one sends one, you can do that. So the botnet is very powerful. They do Bitcoin generation, all kinds of crazy stuff today. So they want to gain access to your machine. they want to gain access to private information. This is why the mobile vector is so interesting today, because think about the stuff that's on your phone. There's a lot of interesting and valuable material there. I mean, think about the passwords in your browser of your phone, for example. This is a particularly interesting one that's been happening a lot: to punish and embarrass individuals and institutions. For over a year, Sony got basically owned by attackers. And before that, the Church of Scientology was treated pretty poorly by the attackers and et cetera. So this is something that they want to do. Also to educate and advocate. You remember Firesheep was released last year? It was a tool that made it really easy to take over a Facebook account on an open network by snooping for the cookies that were coming over the air and then hijacking those sessions. The purpose of that tool was not to allow people to hijack Facebook. The ultimate purpose of that tool was to make it so easy that the solutions that already existed had to be deployed. And then finally, to earn a reputation in the hacking community. So to make yourself a hacker instead of a script kiddie. In the black hat hacking community, they call them the black hats and the white hats, right? The white hats are security people that don't do bad things. The black hats are those that do bad things. And not to be confused with the gray hats, which are in the middle. But you can earn a reputation by cracking various things. Example is like GeoHot from last year breaking the Sony encryption system. So as a developer, given that these attackers are coming after your machine, the goal of the developer is to win the bear race. Now, what's a bear race? You're in the woods, there's a crowd of people, and all of a sudden a gigantic grizzly bear comes through the woods. Do you need to run faster than the grizzly bear? No. You need to run faster than the slowest person in the crowd. And that is ultimately the goal of protecting yourself from attackers. Make yourself less attractive than other targets. So, how attractive are you? Well, that's really a pretty complex function. What is the value of your target? Well, how easy is it to attack is very much a part of that equation. If it's easy to attack, let's attack. How many of them are there? A system that is extremely hard to attack, but there are hundreds of millions of them, is a great target. So if your population gets large enough, ease of attack is not even a part here. What's inside there that's very interesting to get? And how much goodwill does your institution, right? Sony got attacked. Probably the Red Cross isn't going to get attacked because they've got a lot of goodwill. So it's a very complex function. Your goal as a developer is to try and make yourself less attractive than these other targets. Now, developers, we have some control over this. We definitely have control over this. So we're going to talk a lot about that. This is more in the executive suite where that happens. So the goal of this tutorial today is to just give you a basic understanding of computer security and the work that goes on in that field. And we're going to have special emphasis on open source tools that you can start using today. I've got lots of pointers to more information in here, so if you want to continue reading. And then also, I've got a 5-day version of this course that I give, so I'll make those slides available as well, which is a much more detailed version of the slides. And then really, just in an hour and a half, you should be equipped with enough knowledge so you can go talk to people in your institution that are the security experts. Hopefully you've got some. Otherwise, you can be on the way to become that person. A little bit of information about myself. I'm a professor of computer science at University of Michigan in Michigan, United States. I got a PhD in CS, and I work in computer engineering research. My background's in computer architecture, and for years I actually worked at Intel developing hardware systems. And that really gave me a taste for fixing broken things. Because when you work in hardware design, the thought of having something that's broken is so scary. It's so expensive to fix. They put so many resources into making sure that something is not broken. And so I got very interested in finding more automated ways of making things not broken. And then that interest of mine eventually led to the software world as well. And since about '94, I've been working in automated debugging techniques. So techniques to try and find bugs in your software and fix them or illuminate them to developers in a highly automated fashion. Now ultimately, fixing bugs is the process of hardening a program against security attacks, because the vast majority of security attacks are taking advantages of bugs, and we'll see some of those today. So 4 parts of this. First, we're going to do some security basics. We're going to look at what are the tools of a secure system, for building a secure system, and then what are the attacks perpetrated on those tools. Then we're going to look at some security exploit prevention techniques. What can you do to a system to make it harder to attack from a software perspective? Then we're going to look, even after you're really good at these first 2 steps, we're going to look at a really interesting area of security called the side channel attack, where even though you've been very careful to design your system so that it cannot be attacked directly, it leaks valuable information. And we're going to see how a system can leak information and how we can gain secrets from the system. We're going to spend some time looking at that. And then we're going to look at some open source tools that we can use to help build more secure systems. Acknowledgements. Valeria, who presented the fault-based attack work this morning, this is collaboration with her and also my colleague, Seth Petty. And then many students have worked on some of the stuff I'm going to present today. And then also I got a lot of slides from a lot of different people here to help me with this presentation. All right, so let's look at security basics. Now the basics of security, the basic mechanism we're going to use is cryptography. That's the way we're going to hide information. That's the way we're going to build an authentication strategy, a way to prove identity. And then we'll look at some attacks. All right, so cryptography is built on this notion of encryption. Encryption is a process where we can take some plain text, a document, a stream, a network stream, a file, and we can send it into a mathematical function which has as its input that plain text and a key. And the output of that function is something that looks completely random. The more that looks like a random number stream, the better the encryption algorithm is. So the same kind of tools that we use to evaluate random number generators, we also put the output of our encryption into, and hopefully it says, that's a great random number generator. That's the reality of good encryption. And then we're going to send that through some medium to somebody else. And people may be able to listen. People may be able to get into the middle of that communication and muck with it. So there's lots of different, what they call attack modes, ways that they can mess with this information. And when it comes to the second function, the decryption function, the more strong the algorithm is, the more likely what we get out here is the original plain text. Now we're going to need a second key for this decryption algorithm to produce that original plain text. Now sometimes these keys will be the same, sometimes those keys will be different, and whether or not that's true really decides which kind of encryption algorithm it is. Now when the keys are the same, we call that a symmetric key algorithm. Another common name for this is a bulk encryption algorithm. So we get our plain text, we have some private key X, which encrypts the text, and then we have another decryption phase which takes the same exact key and decrypts it into that plain text. So the sender and the receiver share a private key. Anyone who knows that private key can listen into this conversation and can even change the data as it's going through. It's often called a private key cipher, and examples of this are the AES, the US Advanced Encryption Standard, the older DES, the European Standard Blowfish, etc. So these are very useful algorithms. They're particularly useful because they're efficient. They run very fast. This is kind of the core of the AES algorithm. It's an integer algorithm, so it runs fast on normal hardware, and it's composed of what are called rounds. And basically what these rounds do is they swizzle the bits in a fashion that is a function of the key bits. So we put in key bits, we go through these rounds, and the bits move in a direction that is exactly based on the input key. if you can give the input key to the decryption algorithm, if you run all those rounds, the key bits will be back in the original location and you'll get the value out. Now, AES works on 128 bits at a time with a 128-bit key. And it's a very good algorithm. I'm going to show you an attack on it today, but in general, it's considered a very strong algorithm. It hasn't been subject to too many attacks yet that weren't fixable. Now, the problem with using an algorithm like AES to do your normal point-to-point secure communication is you have the problem of how do I share my private key with the other person in a way that's secure, right? Because until we both have that private key, our communication has to be in the clear. So, you know, have you ever done this before? You've zipped up a file with a password and you email it to your friend and then you email in another message the password in the clear and say, okay, now decrypt it. You know, not a very secure technique. That's what you would have to do with a bulk encryption algorithm like that implemented in the ZIP algorithm. And so enter asymmetric key encryption. And this is the tool that is used to share a piece of information between two people when they have no shared common secret. The way it works is we've got our plain text and two keys. One key is called the public key and one key is called the private key. Now, the receiver distributes their public, they actually have two keys. The receiver, like your bank, for example, has a private key and a public key. Now, the public key, they say to everybody, this is my public key, this is my public key, this is my public key. And the private key, they lock in a vault and they put some dude, you know, a mall cop next to it that cannot, you know, nobody can get access to that key. That system is secure, it's private. If anybody gets access to this key, the whole system breaks down. Now, the way we can share information privately is I can grab your public key and I can encrypt that data with the public key, excuse me. If I encrypt the data with the public key, the only key that can decrypt that data is the private matching key. So if I have the public key of the bank and I encrypt data with that public key, I know only the bank, assuming they haven't given their private key out to anybody, can see that information. Now, using this, I could, for example, send my bulk encryption shared key through that channel. So it's a very powerful thing. Typically called a public key cipher, and examples are RSA algorithm as well as Diffie-Hellman. Now, using this mechanism, you can implement something called authentication. Authentication is the process of determining if the person you're talking to is indeed the person you think that person is. And we can do that with this algorithm. So let's say I want to talk to my bank. The bank holds the private key and they distribute the public key. I want to talk to my bank. And so what I do is I take a message. It doesn't matter what that message is. Just a piece of information I generate myself. And I send it to the bank. And I ask the bank to encrypt it with their private key. Now, the opposite is true. What can be encrypted with the public key can only be decrypted with the private key. What is encrypted with the private key can only be decrypted with the public key. So if I ask the bank to encrypt a message that I generated with their private key, and then the bank sends it back to me, and I decrypt it with their public key, and I see the same message, what does that mean? That means that the holder of the private key had to have encrypted this message. And if the private key hasn't been compromised, I'm indeed talking to my bank. I am talking to my bank. And that's the process of authentication. One other interesting problem here is, how do you distribute the public keys? Anyone know? Yes?
How you done? You screwed?
What?
It's a very hard problem.
It's a hard problem. The main solution in the commercial world is there are a few entities which sign public keys and say that this public key belongs to this institution. For example, VeriSign. they sign it with their private key. Now, how do you get the public key of VeriSign?
Well, they and their 600 odd buddies, you just trust them implicitly?
Also, yes, one way. But in general, Mozilla encodes that into your browser. It's in Safari. You trust your browser. And that's where those public keys are. So, and that's called the chain of trust. So that's authentication. That's a very powerful mechanism that lets you know you're talking to whoever you think you're talking to. Now, these asymmetric key ciphers are amazingly powerful. Why don't we just use them? They're about 1,000 times slower than the symmetric key algorithms. So you don't rely solely on that. You only rely on it for authentication and sharing your private key so that you can switch over to the faster, less computationally heavy symmetric key ciphers. So let's take a look at SSL, the most common secure sockets layer implementation on the internet. This is a way to authenticate and communicate with another party in a secure manner. This is time going down, and these are the messages going across between the client and the server. Let's say the server is my bank, and this is my client, this is my browser. So the first thing the browser does is it encrypts its symmetric key that it wants to use for bulk encryption with the server's public key that authenticated and for its bank. It then sends that message to the server. The server decrypts it with its private key to get the symmetric key and then returns a finished message that's encrypted with the shared symmetric key that was passed in that original message that was encrypted with the public key of the server. Now, when that comes back to the client decrypts with the symmetric key it sent originally, and if it says finished, what does that mean? It means that this message was prepared by the holder of the private key matching the public key I originally encrypted with. That's authentication and then bootstrapping a symmetric key algorithm. Now, the client, my browser, has a symmetric key, the server, the bank, has a symmetric key, and then boom, we just start executing back and forth with our symmetric key. We have a secure channel that's efficient. All right, so, and then here you can see some performance analysis. This is based on an SSL session length. How much time do we spend in the public key algorithm versus this application, the browser, versus the private key algorithm? And you can see the crossover point is about 16K bytes of session data. If you send more than 16K bytes of session data, it's more efficient to do a public key encryption and switch to the symmetric key. All right, so that's authentication. Symmetric key algorithms, asymmetric key algorithms. Let's take a look at a few other details that allow us to build what's called a stream cipher. Up until this point, we've just seen a way that you could take a piece of data and encrypt it and send it to someone else, and it's a fixed length piece of data. But often we want to do a stream of data, a file, a codec output stream. We're talking to someone over a SIP network, for example, and we want to continually encrypt a stream of data, which we may not know how large that data is. So we have to have a streaming cipher implementation with the underlying encryption algorithm. And in general, there's two approaches to streaming ciphers. The most simple approach is called electronic code book, ECB, where all we do is we take the first piece of data, encrypt it, and send it, take the second piece of data, encrypt it, and send it, third, etc., etc. It's very efficient, has tons of parallelism, and as you'll see in a little bit, it's the weakest kind of encryption you can possibly do. Which led to the development of what's called CBC, cipher block chaining. And what cipher block chaining does is it takes your first piece of data in the stream, encrypts it, and then XORs the result of that with the input that's next to be encrypted. So you're chaining, you're always taking the output of this and encrypting it with XORing it with this new value, and then encrypting that, and then XORing this value, etc. And then to decrypt, we'll decrypt the data, and then XOR the output of the next one with the previous piece of stream data. Now here's the advantage of this. Now this is an image that I encrypted with ECB and then an image that I encrypted with CBC. And you can see, this is not as strong as this. The reason why it's not as strong is because it essentially becomes a problem of substitution to figure out how to decrypt the algorithm. Every time I have the word "the," it's going to be the same in the output with the unchained cipher. With the chain cipher, the first "the" is going to be dependent on what came before it. The second word "the," when it's encrypted, it's dependent on a whole other piece of information behind it. So we never see any correlation between the input and the output like we do with electronic code books. So, you want to avoid electronic code book, you want to go to CBC. The main challenge there is there's no parallelism in CBC. In fact, if you have parallelism in your encryption algorithm, it's not a good encryption algorithm. A definition of a good encryption algorithm is if I change any bit in the stream, all the bits that follow it change with probability 50%. And that means there's no parallelism. And that's a big challenge for making efficient encryption in systems designed today. Then one other thing, yes?
Can you just explain parallelism?
So parallelism is the property that computation has subcomputations that aren't dependent on each other. So for example, if I have a multi-threaded processor, if I have the processor on this laptop, for example, has 2 cores. If I have parallelism, I can use both cores to run the algorithm and to do the encryption. But if there's no parallelism, there's nothing to share, and so I'm stuck running on just one core. So parallelism is a way to make software run faster in a world with multi-cores, which is the world we live in today. And unfortunately, that's not the case for encryption algorithms. They don't have parallelism if they're good algorithms. And then I want to leave you with one other really useful tool from the encryption toolbox, which is the hash function. Now, hashing is a way to ensure integrity. It's a way to make sure that nobody mucked with something. Nobody twiddled some bits. Nobody changed the value. A good place, if anyone's got an iPhone, it uses hashing like crazy. It will not run a piece of software that's been twiddled with unless you jailbreak your iPhone. Now, how do they know whether or not you twiddled with your software, added maybe a nice tethering application to it? How do they know? That through the use of hash functions. So a hash function is, it's a function which takes a piece of information, like Shakespeare's complete works here, and crunches it down to a single fixed length value. In this case, 128 bits. And that value is correlated with this input. Now, what's really cool about a hash function is the probability of finding another value at the input that produces the same output is 1 over 2 to the 128th, which is essentially impossible. You can't search that much. So if I have a hash function and I hash your data and it doesn't match this function, then I know that's bogus information. That's not what I thought you were going to run on your iPhone. But if I hash this piece of information and it matches this value, I know that that's the information I left on your phone with probability 2 to the 128 minus 1 over 2 to the 128. And that's a pretty good probability. These hashes are nice because they're fixed length. They're easy to work with.
Can you just say that expression again? Probability.
Oh, the probability that it is what you left there is 2 to the 128 minus 1 over 2 to the 128.
I didn't hear the parentheses.
Now, the iPhone actually combines asymmetric key encryption with hashing. Now, how do we know the hashes that are on your iPhone are blessed by Apple? How? Signed with the private key of Apple. That's the authentication process. When you make an iPhone app and send it to Apple, they look at your software and then they sign your binary with their private key. They sign the hash of your binary with the private key. That gets installed on your machine. It won't even put a hash on the machine that doesn't decrypt properly with the public key of Apple. And so by combining asymmetric key encryption with hashing, we can now do what's called attestation. We can make sure everything on the iPhone is blessed by Apple. The process of jailbreaking is removing the attestation check. All right, which is hard to do because the first piece of attestation in the iPhone is the ROM. And so it doesn't even go into the ROM unless it passes this test. So the way they jailbreak an iPhone is they have to find a bug to exploit to overtake the ROM. All right, so great examples of these algorithms are MD5, which is no longer considered useful because it's fairly easy to find values that map to values that are specified. So it's cryptographically broken. People should stay away from MD5. And so today, sort of the algorithms here are SHA-1 and SHA-2. Now, cryptographically broken. This is an interesting term. And in general, everything becomes cryptographically broken. In the world of security, everything has a shelf life. The longer it sits up there, the longer we use it, the more time it gets to be attacked, the more the community of researchers and attackers can figure out how to compromise it, and pretty much everything falls eventually. RSA's done pretty good, 24 years. So that was a good one. All right. Now, as a programmer, these hashes are really useful, even if you're not doing security stuff. But I'll show you some security applications. Password storage. If you ever go to a website and say, I forgot my password, and it sends you a password back, that's a bad website. Why? Because it's storing your passwords. What's better to store is the cryptographic hash of your password. Because if I send you back the cryptographic hash, it's a probability 1 over 2 to the 128 that you can figure out what the password was. So it's a very useful tool to hide information, to authenticate your password without actually knowing it.
So you were saying MD5 is broken. A lot of people have MD5 passwords in the shadow.
Yes.
Does it mean that anyone who has enough computer can now generate random strings that map to that?
Yep, they can, but the easier approach is to use what's called a rainbow table,
Right.
which is you take the most common words and just map them.
Yeah, I don't mean like if I have a strong password.
It is true. It is true if you're using MD5 encryption in your password file. It's pretty easy to not know what the passwords are, but to create new passwords that do work.
Okay.
Yeah. Yeah, so you definitely want to make sure you're using SHA-1 there. Okay, so that's a useful application. But you can use these hashes elsewhere. For example, let's say you've got a database on a web server, and you're going to do queries to that database. Instead of sending the large chunk of data to users that have already asked for it in the past, say, what's the version you have previously? Send me the hash. And then I'll see, and then if it matches, I'll say you've got the latest version. If it doesn't match, I'll send you that big blob of data. So a hash is just a really useful tool in programming. All right, so that's some basic tools in the toolbox of the developer to build secure systems. Now let's take a look at how we can attack these systems. And what I want to do here is, there's just thousands of different kinds of attacks, but I want to demonstrate the software security arms race. So we're going to look at an attack, then we're going to look at a way to prevent that attack, then we're going to look at an attack that thwarts that, and we're going to just kind of climb up that ladder and see the process of compromising and recompromising a machine. So security vulnerabilities are everywhere. They cost a lot of money. The US National Institute of Standards and Technology, they estimated $60 billion a year lost due to security attacks. And a pretty steady climb over the years. This is CERT, institution out of Carnegie Mellon in Pittsburgh in the US that tracks vulnerabilities in software. And it's a pretty steady climb in terms of the number of vulnerabilities out there. And of course, systems like Windows are highly vulnerable. It's kind of the whipping boy of the security world. But even Linux is vulnerable too, and becoming more attractive to attack because there's so many forward-facing Linux machines on the internet. Yes.
Are they fixed bugs?
Are these fixed?
What's the metric? Is that the ones that we...
These are fixed. Yeah. Oh, these are the fixed ones, but those aren't the good ones. The good ones are called the zero-day exploits. These are bugs the attackers know about, but the vendors don't. So there's no protection against this other than, don't put your machine out on a public-facing network. And even embedded devices like RFIDs can be compromised. Or Karen Sandler's pacemaker, as we saw this morning. So let's look at this is the granddaddy of attacks, the buffer overflow attack. Very popular. The original, Morris Worm used this attack, and even today, this attack is very useful. Most attacks are built on this basic approach for attacking a system. And it relies on the way we store information, temporary information in functions. Now, the way functions work, when you call a function in software, it allocates a buffer on a stack. A stack is just a piece of memory that we allocate and deallocate as functions are called and returned. If I call two functions, return one, call another. So it operates as like a stack of plates. When we call a function, we put a plate on the stack. When it returns, we take it off. Now, the most important part of the stack to the attacker is, on the stack is the address of where I got called from. So that when I return from a function, I go to that place and I look at that address and then I jump to that address. So the goal of the attacker is to change this value. The way they change this value is they look for some sort of variable that is of the type array. What's an array? An array is a variable that contains many copies of a variable inside of it, and so that I can index it. I can say, write to the 5th entry, write to the 10th entry. And programmers often don't check to make sure if you're not writing past the end of the array. It's a fixed size. And so if you write past the end of the array and the programmer doesn't check, then if there's an array here, I can write there by just giving it a big number. And if I can write there, I can cause it to jump to here where I wrote in the array. And that's the basic approach. So I'm filling this buffer with information. Usually it's going to be some sort of network read. Now the programmer assumed when it says in the manual that a JPEG line can't be bigger than 2048 bytes, I assume nobody's going to violate that rule. But somebody crafts up a JPEG that's got 4096 bytes in a line. And the programmer doesn't check. And so boom, it just blasts past the end of the array, overwrites the return address. And the programmer's clever. The programmer points it back into here and basically jumps to a program which is contained within the line of the pixels of the JPEG. Now what does that do? It puts you in the botnet and then starts running your program again. So it just kind of surreptitiously takes over your machine. So it's a gradual process.
Just by looking at a JPEG.
Yeah, I mean, there's so many JPEG exploits. People love those because you go to a website and you're owned. You just display the page.
For a while, there was when Miles 4 was released, the first release route for it was if you visited the web page, there was a PDF export route over.
Yeah. Oh, PDF. Oh my gosh. PDF's the number one vector. We're going to see the vectors in a little bit later. So now we're in the botnet. But there's a lot of other ways to do buffer overflows. This was an attack on Bind last year. And it's Bind is very nice because it runs on multiprocessors, and it can you can have multiple Bind servers, each one running on a different processor. So if you have lots of processors, you can do a lot of DNS services. And this is a bug where what would happen is that there wasn't correct synchronization between two threads, and it was possible by just hammering on a Bind server to overtake the server. So there's a case where it checks to see if some pointer that it wants to write into is null. Then let's say there's a thread switch. The second thread checked to see if its buffer was null, then allocated a very large buffer, or small buffer, and then we came back over here and rewrote that pointer, and so now this guy writes into the correct buffer, but now when we come back here, this thread doesn't know that this pointer got changed. There was no synchronization on that variable, and now it overwrites the other buffer too far. Very clever attack, relying on the asynchronous nature of parallel programming. And if you've ever done parallel programming, you know how hard it is to know where to put all your locks. So this is a really great attack. All right, so buffer overflows everywhere, cats and dogs making love in the street. It is a wild place out there. So what do we do about it? Yeah.
How do you actually discover that this was the attack that got used?
How do you discover? Well,
I assume they don't tell you.
no, usually what happens is while they're trying to craft the attack, they're dumping core all over your machine. So in the IT world, if you see in lots of cores, someone's crafting an attack. Because one of the things you got to do is you got to figure out what is that address that I go to so that I actually hit my buffer. That address isn't told to you, it has to be discovered. And in the process, you're dumping core. All right, so the first thing that they did is they introduced what's called the NX bit. We'll see that in a little bit. The NX bit is no execute on stack. No code on the stack may be executed. So that when you define a stack page, you say no execution on this page. Okay, now they're thwarted because remember, we put the code in the array and then jump to it on the stack. If you can't jump to it, you're done. No. Enter the heap spray attack. Heap spray attack is what's called a blended attack. It's two attacks combined to implement a single takeover of a machine. It uses a buffer overwrite, but because the buffer overwrite cannot execute on the stack, it's got to jump to code in the heap. So how do you make sure that you jump to your code in the heap? Fill the whole heap up with your code. Now, how do you fill the heap up with your code? The most common technique is to get someone to go to a page that executes JavaScript that just starts allocating massive number of strings and holding on to them in some chain so they're not reclaimed by the garbage collector, and you end up with an entire heap filled with code that can take over the machine. Then you jump to a random address in the heap. The probability that you hit your code is proportional to the amount of injection you did in the heap. So if the heap is 99% full of your injected code, the chance you're going to hit your injected code is 99%. Very effective. Nobody executes on the stack. Yes?
Can you explain the distinction between the stack and the heap?
Yes. The stack is where we put our temporary variables for programs. So when we call a function can have variables, and those variables are kept on the stack. The reason why those variables are kept on a stack is because programmers love to do crazy stuff like recursion. Recursion is a function that calls itself. The classic one is factorial. And so as a function calls itself, it needs a new copy of those variables. And so the stack is the way we make all those copies. The heap is a place to allocate storage where the lifetime of the storage outlives any single function. That's where you put your database. That's where you put your options for the program. That's where you put, configuration information that has to live a very long time. It's also the place where the jitter puts the code that it generates, etc. So it's a different part of the system, and it's also something that's terribly difficult to make not executable.
The heap is what you get from malloc, right?
Yep, it's what you get from malloc.
Why would memory allocated via JavaScript be marked executable? It's an interpreted language, it shouldn't be.
What? Okay, say it again.
Why would memory allocated via JavaScript be marked executable?
Because the entire heap is allowed to be executable. So it doesn't discriminate. I mean, if you had a very smart, probably the approach would be to have a very smart jitter that put its data on some pages and its code on other pages. But they haven't done this yet. So, yeah.
But why is the heap executable? It's supposed to be data, not code.
The heap's executable because if you're running JavaScript, you're jitting code. You're creating code as you see it come from the internet. When you download a JavaScript piece of code, it compiles it to x86 or PowerPC or whatever. It has to store that somewhere. And it has to store it in a variable size heap. Right. So you need to execute out of the heap.
That's true for that in Java, but most times you don't generate code on the fly.
Right.
And
so
the heap is still executable, right?
So like V8 on the
yeah, you could be clever. Systems could be more clever and say this is executable heap, this is not, but they don't yet.
Okay.
All right, so what's the next thing you can do? This morning, Karen talked about voting machines, and that's a particularly place where they're really paranoid about security. So enter a voting machine. They don't want to have heap sprays. They don't want to have buffer overflows. So that in the United States, the city of DC built a voting machine that had no ability to inject code in the machine. It would only execute code out of the ROM. The ROM was not writable. There was no way, and still, no one has found a way to inject code into this machine. The machine was pwned. Here's how it was pwned. It was pwned by what was called return-oriented programming. Again, you need to have a buffer overflow attack. But this time, we don't just write a single address to jump to. Instead, what we do is we examine all the functions in the machine. And we take the functions and we create what's called a return-oriented program. We say, I want to implement X. And I can implement X if I execute the last 3 instructions of this function, and the last 5 instructions of this function, and the last 4 instructions of this function. And so then what I do is I write all of my stack frames as I would want them into memory, so that when it returns, it jumps to my sequence of returns. And those sequence of returns are not functions, they're the ends of functions which constitute pieces of code that can actually do what I want. Now there was a team out of Princeton University that with this single voting machine had 128K ROM. They built a Turing-complete machine out of the tails of functions. What does that mean? That means they can implement anything that they want to on that machine. They have a full programming language. So this will give you a sense of this climbing the arms race ladder. You think nobody can put code into your machine? We don't need to put code into your machine. Yes?
How can you stitch the 2 bits together? Normally, once you return, the control just goes there and...
So what you did is you injected a new set of stack frames. So where you would originally have returned to the caller, you returned to the tail of some other function, and when you hit the return of that function, now you see the next frame that I injected, and the next frame, and the next frame. So I've set your local variables, and I've told you where to go to next.
So you can only use the end of functions?
Only the ends of functions. Yep. All right. So pretty powerful technique. So, and just to give you a sense of this, security is not a destination, it's a journey. Right? You've got to be constantly vigilant. Here's some other interesting stuff. These are hardware-based attacks. Hardware-based attacks are especially hard, they're especially concerning because it's very difficult to fix them. And there's been a number. Here's an example of somebody who published a remote code execution exploit that was based on an Intel CPU bug. Worked on Mac and Windows. So it was machine independent. Here's another demonstration where there was a researcher in Illinois in the United States who added 1,400 gates to a design. So he was pretending to be a rogue designer on an Intel team. Added 1,400 gates, tiny little bit, like 0.001%, and built a Linux backdoor on a system, just with that little piece of hardware. So lots of other examples. All right, so there's more reading. Now let's move on to the next part. So we've seen some exploits that that people have perpetrated on us. Let's take a look at some techniques to prevent or thwart those exploits. We're going to look at no execute stacks, address space layout randomization, stack canaries, encrypted pointers, my favorite, sandboxing, and then safe languages like Python and Java, etc. We're going to look at those. All right, so let's look at the no execute stack. The idea here is when we define memory in a program, we have this virtual memory system that allows us to put permissions on memory. Traditionally, the permission has been, you can read, you can write. Well, let's add a new permission which says you can or cannot execute. Now we can create pages where you cannot execute, and we can mark the entire stack we're not allowed to execute. Most microprocessors since about 2005 support this facility, and it's used pretty widely today. Linux implements it quite nicely. Now we saw the easy thwart around that is the heap spray attack. So how do we get around the heap spray attack? Well, where's the heap? That's what you got to do. You got to move the heap. And that's through what's called address space layout randomization. Mac OS X, Windows 7 and later, and for quite a while in Linux, they've implemented address space layout optimization. Now, every program expects its memory to have a number of different spots. It expects to have a stack for storing its local variables for functions. It expects to have a heap for putting long-lived data. It expects to have an area to put its global variables, and it expects to have a place to put its code. Fortunately, what it doesn't expect is where that stuff will be. So every time you run a program on Linux, the location of those things changes randomly and dramatically. Now, why that's so important is remember this jump. This jump. This jump means I got to put an address here that jumps to my code. In the old system where I was always in the same place, I could just say, try this address, no, try this address, no, try this address, yeah, I own your machine. Go to all the other machines are the same way. With address space layout randomization, that address changes every time you run the program. So now the probability isn't, it's not a binary search to figure out where it is. It's 1 over the size of your address space. If you're on a 64-bit machine, 1 over 2 to the 64, that's a pretty long shot. You're not going to find that address. And when you get one machine, the next machine is just as hard. You have no information there. It's putting its stuff in random addresses.
So it's only the jump that fails. The programs still get buffer overflow and still crash.
Yeah, they crash. But it's hard. You don't know how to get to your injected code. And so really the attack on a machine with ASLR requires a read hole. It requires the ability to read data and return that data and find where your code is being injected. Also, heap spray can have some effect on this. But in general, attackers don't want attacks that fail with high probability. Because when they fail with high probability, they get discovered. And when they get discovered, they get fixed. Now, your grandma still probably didn't patch, and we could still have her machine, but we're not going to get, we're not going to get as many machines as if our exploit is unknown by anybody. So ASLR is a very powerful technique and implemented widely. Heap spray can get around it to a certain extent. All right. Now here's one of my favorites, stack canaries. OpenBSD implements these. They're not in Linux. Stack canaries, what you do here is, now remember, these are our frames. When you have an array here, to get to the return address, I need to write off the end of the locals, and I need to go to overwrite that return address. So all a canary does is it's a random piece of information that changes every time I run my program. There's a known, as I start my program, it picks a canary, so I can't overwrite this with a known value. It's a random value. And before I return from a function, I look at the canary, and if it's not the right random value, I don't return from the function. I stop. Because I know that someone attempted to overwrite my return address, and with a buffer overflow, I have to overwrite this value. If this value is random every time I run my program, you've got to guess it. Unlikely you're going to guess it, and that saves me. OpenBSD does this, and that's why OpenBSD has such a great reputation for being difficult to hack. It's hard to inject code in that machine.
I think that's actually in recent GCCs as well.
Yeah, I'm going to talk about that. You can put it into GCC as well. Oh yeah, and I'm going to show that ProPolice later. We're going to look at that. All right, so now I love this one even more because this protects the pointers directly. Let's say I have a read attack. In this one, if I have a read attack, I can figure out what your canary is, and then I can overwrite your buffer. So I need a blended attack. I need to know what this value is, and then I can overwrite. Encrypted pointers are very interesting. What we're going to do is every time we write a pointer into memory, we're going to encrypt it using an XOR typically with a value that was picked when the program started running. So pointers are all encrypted. And if I want to inject a jump into your machine, I need to know the encryption key, which is going to take some sort of blended attack. So here, I have a pointer in memory. When I attack the machine, I overwrite this pointer with a value to jump to my attack code. If I encrypt those pointers, then if I overwrite with a value, it goes to some random place. A very powerful technique. And there's a tool called PointGuard. It's not an open source tool, but there's a tool called PointGuard that implements this. Very nice approach.
Is that a compiler feature or is it a language preprocessor?
I believe it's a post-pass on Windows compilation. It manipulates the program before it generates binary.
So it's after the compiler.
After the compiler, yep. Yes.
So just to, the address-based randomization has a trade-off in memory. The Canary has a trade-off in instructions.
Yep.
And this has a, and you gave percentages for those. What's this one's trade-off? Like it's extra cost, CPU overhead?
CPU overhead, about 20%
Okay.
is what you pay.
But STR doesn't cost memory, but it's virtual memory.
Yeah, I understand.
Yeah, it doesn't cost a lot. Yeah, it's virtual. Another technique which is popular is sandboxing. And here you want to imprison violators before their first offense. The idea here is think more broadly. What happens when you overtake a machine? You've successfully done a buffer overflow. You've injected code. You now own the execution of the machine with code that you injected. Well, at that point, you're going to try and write, you're going to try and replace init. You're going to try and replace ls. You're going to try and replace login. All kinds of executables. So let's let the attacker attack the machine, but let's put a set of rules on what this application can do. And if the application violates that set of rules, if the application tries to write to the login executable, then I will terminate that application. And that is the goal of sandboxing. This is what Chrome does. This is what Firefox does. This is what IE9 does. For each one of your tabs, it lives inside of a sandbox. So here's Chrome's sandbox architecture. Each one of the tabs in your Chrome browser is a process. Those processes are not allowed to talk to the operating system. They have to talk to the Chrome Policy Manager. The Chrome Policy Manager is continually evaluating what is this tab doing. Is it trying to talk to another tab? Then it's got to go through my policy on how to do that. There was a great attack a few years ago called the browser in the middle attack, which was, if you went to this one car forum and you had a tab open to some bank, HSBC. If you were logged into your HSBC bank account, it would transfer $1 from your account to their account every time you went to a new web page. And the reason why is because the JavaScript inside the car forum was infiltrating the tab on the HSBC bank login. And they got a lot of cash out of that. So you can't do that here because any communication between these tabs has to go through the policy engine, and then there's a very strict communication link between those different tabs. They can't share address information, for example. And so it's a way to try to, once the attack happens, make it innocuous as possible. And a very effective technique.
So you're saying that before Chrome, JavaScript on one tab could talk to another tab on purpose?
Yeah.
Or was it debugged?
It was on purpose and used.
Wow.
It was incidentally allowed and then used as an attack. It's called the man in the browser attack.
Seemed like a good idea at the time. Huh?
Yeah.
Okay.
Today they have some very strict rules on how tabs can communicate. All right. So So perhaps we should go to the root of the problem. What is the root of the problem? It's that buffer overflow. You know, and a lot of people advocate going to safe languages. Safe languages eliminate these two basic problems. The buffer overflow, the spatial buffer overflow, that's where you have some array variable and you have the ability through a bug in the program to overwrite past the end of it. C allows this. C++ allows this. Java doesn't. Python doesn't. Ruby doesn't. There's no way to overwrite the end of an array in Ruby unless there's a bug in the underlying implementation. The temporal buffer overflow. This is where you have a buffer, somebody frees it, but through an old pointer, we can still write to that. There may be a new variable there that we can access. C allows this. C++ allows this. Java doesn't. Java does garbage collection. If you're still referencing your variables, they're still owned by you. Ruby, Python, etc. do garbage collection. You can't do this. So a lot of people have advocated, let's get out of these low-level programming frameworks, move up to what's called managed code, code that runs on virtual machines like Python, Java, etc., and get rid of these buffer overflows. So, you know, is that a good idea? Well, certainly you prevent all the buffer overflows, but in general these languages are much slower, which is okay to a certain extent. But here's an interesting set of statistics. When I made this slide in May 2011, I went to this site, Qualsys. They track the top attack vectors. An attack vector is a specific program that's being attacked. Look at the top two, Adobe Flash Player and Oracle Java. The top two attack vectors are safe languages. Adobe Flash uses ActionScript, which is just a small delta off of JavaScript, which is a safe language. Oracle Java is Java, and that is a safe language. The two most popular attack vectors, the two ways that attackers were getting into machines were attacking Java and JavaScript. Why is that? The language is safe. Yes, the language is safe, but the underlying implementation is broken. So until those language implementations becomes stable and correct and secure, that's going to be a problem. But the trends are in the opposite direction. What's been happening in JavaScript? Just-in-time compilation. Huge amount of complexity has gone into Chrome and Firefox and IE9 in the past 2 years because it's now taking JavaScript and translating it to x86 and PowerPC, etc. ARM. That translation process has got bugs in it, and those bugs can be exploited. So even if you've got a safe language, it can be exploited. Now eventually those languages are going to stabilize and become more secure. At that point, we'll have a better option here. But until that point, safe languages just are not a panacea. But if given a choice, why not choose the safer language? So definitely consider that. All right.
How much was it implementation bugs as opposed to sandboxing errors?
Pretty much all implementation bugs.
Sandboxing was well done. Which was the implementation?
There's only been one exploit that I know of in like the Chrome sandbox, and there was a lot of finger pointing because it was an interaction with Flash, and Chrome said this is not a bug, this is a Flash bug, and then Adobe said it's a Chrome bug. But so sandboxing has worked pretty well. All right, so now I just want to tell you a little bit about my work, which is in the area of security vulnerability analysis. The idea behind security vulnerability analysis is we are going to find the bugs that the attackers are exploiting and fix them. And we're going to do that in an automated fashion. So I just want to introduce this to you, and then later we're going to talk about some open source tools that can provide this facility to a certain extent. But first let's take a look at the development cycle and see how it differs from what I think is a more ideal cycle. We develop our applications, we distribute them to our users get hacked, we debug our users' hacks, and then we develop fixes around those and go through the cycle again. This is how we build secure software today. For every piece of secure software out there, there's a trail of users that have been abused. That is unescapable in today's world. So you've got upset users, you've got embarrassed developers, and in a sense, it's not a very good approach to software development. The alternative is to employ security vulnerability analysis. Where you develop your application, you employ some tool that actively looks for bugs that might exist. And we're going to look at one very simple example of this. Then we debug those problems without giving it to our users, continue development, and when we feel we've got all the bugs, we give it to our user. Unfortunately, you never actually know when you're done. That's the halting problem. That's Alan Turing proved many years ago that you'll never know when to stop because of the complexity of programs. But we can do much better than the previous slide. So let's make this real. Let's look at what security vulnerability analysis is. So many of these analyses, what they do is they really take advantage of how attackers attack programs. Attackers look at your program as a giant black box. They do this even if it's open source. Even if they can look at the source, sometimes they don't even bother with it. They look at what are the inputs to this program? What is the information I can feed to this program? And what are the expectations on how that information is manipulated? Violate those expectations and see if you can derail the program. That's the approach to taking over a program. So a great source of bugs can be found if you can find improperly constrained inputs for a program. If you can properly constrain all the inputs to the program, it becomes very difficult to attack that program. All right. What's great about security vulnerability analysis is it doesn't require an active attack to find those bugs. In the traditional approach of your users getting attacked, you have to have an active attack in the system for it to fail and for you to know that the bug exists. With security vulnerability analysis, you don't need to know what the attack is. It will discover that one can exist. Now that's really powerful for developers. It's equally powerful for attackers. So these kind of technologies are becoming very popular in the attacker community. They will point you at places to attack in a program. So let's look at the simplest kind of security vulnerability analysis. This is the most simple kind, and it's called taint checking. And be sure about this. You want your program's taint to get checked on a regular basis. What is taint? Taint is a property of a variable that it came from the outside world and you never checked it before you used it in a potentially dangerous way. Now, in programming terms, what is danger? Danger is you index an array, you jump through a register on a value that you didn't check. Those are the two most dangerous things. Or you invoke a function on a value you didn't check. So taint checking, what it's going to do is it's going to watch when information flows into your program. And it's going to attach bits, taint bits, to that information. So for example, if you're reading from a network socket, the data you get back from that fread will be tainted. Now, attackers are clever. They know that they're not going to be able to take a piece of information and apply it to directly in some dangerous manner. Typically, you're going to compute on that information, you're going to store it into memory, you're going to read it back, compute on it some more, and at some later time, hopefully then we can perpetrate an attack. So in taint analysis, we also have to propagate taint through computation. If I add two numbers together and one of the inputs is tainted, the output becomes tainted because that output is now under the control to a certain extent by the attackers. Now the clearing of taint occurs whenever you check your inputs. Now what does it mean to check your inputs? An assert statement in languages, a predicate. You check to see if it's less than or greater than. You use some kind of relational operator on it in your programming language. That is assumed to be a check. And that clears the taint on the data. So what it does in the analysis is it says we know which values have been examined by the program before they're allowed to do potentially dangerous things. Now, unfortunately, if the checks are wrong, then you still can attack the program. So this is the most simple approach to checking. And there's other tools which are much more sophisticated and do what's called symbolic analysis and actually try to discover if your checks are sufficiently constrained. And I'll talk about one of those tools later. Now, whenever you do something that's potentially dangerous, you look to see if the value is tainted. If you index an array and the value is tainted, that's a value that came from the outside world that you never checked. That's dangerous. Even though there's not an active attack on the program, I know there's a danger point here. And I can tell the programmer, this line is accessing an array with a value that came from this network I/O, and it never got checked. And the programmer can fix that. That's security vulnerability analysis. Very powerful, very proactive. So let's see a little example of this. Now, before we see the example, now then, this is the not gentle part of the talk. There's two not gentle parts. We're going to look at something called data flow analysis. So we've got a little piece of code here. This code's going to read information from the outside world, and it's going to do a bunch of computation on it. And as I do this, I'm going to create this data flow graph. This is a graph that's built on the fly that tracks how does information flow through my program. And as that information flows, I am going to ensure that the taint information gets propagated properly. But let's just look at the data flow graph first. X produces a value that it sends to this next line of code. So I put in my graph an indication that I sent value to that other statement in the program. This next statement uses a result of Y. So it's a child of this part of the graph. And as we go through the code, we see how information flows from the input to all these different statements. We build that on the fly. To do taint checking, I propagate that taint information down this data flow graph. And if I ever see you validate the information with like an assert, for example, I clear that taint information so that when I do checks in the program, I know this is safe, but these two are not safe. Yes?
Just a question about the example. Why is Z assigned to twice in the other code? I mean, you've got it here with validate.
Oh, that should be a Z. Thank you. Sorry. Thank you. Oh, no, I validated X. No, that's OK. Z is safe because it's derived from a safe value. Yeah, so that's OK. Yes?
What happens with that class of bugs where your program is working fine, but what it's actually doing is using someone else's bit of memory? Like, you know, it's accidentally reading one past the end of its array.
Yep.
Normally when it's not being attacked, that's just a zero and it works fine.
Yep.
Someone attacks it, manages to fill that buffer with.
Yeah. So this will address that kind of bug, the bug where you're reading someone else's memory. Reading someone else's memory occurs because you didn't check if an index to an array was sufficiently constrained. And then the taint will be set on it. And so you'll get an indication as a programmer, you didn't check this value. Oh, I better put a check there. And then I don't get that warning again. So now this only works with buffer overflows, but there's other analyses that work on free and malloc and free and accessing dangling pointers as well. Yep. And we'll look at one tool, Valgrind, which is very, very powerful in this space and can provide a lot of value today.
Does Valgrind tell you that it's the data is tainted?
Yeah, there's a tool. Valgrind's a platform for doing these kind of analysis, and there's a tool, Taint Check, that'll do this.
Okay, right, thanks.
So there's a bunch of tools or techniques we can use to provide more safety to programs. Here's some pointers that you can follow up on, more reading. Now let's take a look at side channel attacks, which are always fun. This is a little bit depressing because you've built a really secure system and then somebody comes in and just basically listens to it, wraps their arms around it, does a little bit of voodoo, and pulls all the information out. So this is the way we're going to harden systems against this is very difficult, these attacks. But we'll see some ways. We're going to look at cache-based attacks, power monitoring attacks, timing-based attacks, fault-based attacks. If you read Valeria Bertacco's talk this morning, you saw one example of a side channel attack, very powerful one. So what is a side channel attack? A side channel attack is, the classic example is, from the old Wild West movies, the person opening the safe using the stethoscope and listening to the tumblers, right? That's a side channel attack. The system was designed so you had to know what the exact sequence of numbers was. But by using the stethoscope, you can listen to the tumblers move into place. And the change in sound indicates the internal state of the system and allows you to attack it. Now, what is the parallel to listening to the tumblers in the electronic world? It's looking at how much current your system draws. The amount of current it draws is a function of the computation it's doing. So if you're doing a lot of adds and multiplies, and the number of multiplies indicates something about the key, I can infer how many ones, for example, are in your key by how much power it draws. How long does it take to execute? Classic attack on RSA, where the original implementations of the algorithms, they would go down and they would see, wherever there's a 1, I do exponentiation. Wherever there's a 0, I don't do exponentiation. So that the delay in the response of the encryption was a function of the number of ones in the key. That's a huge amount of information. You don't know which ones are ones, but you know how many of them there are. And that really reduces the search space. Electromagnetic radiation. There's tools that can listen to the noise out of a keyboard, the electronic noise out of a keyboard, and read what are you typing. There's other tools that can listen to the scan line refresh on old monitors and know what it is you're looking at. That's noise, that's electrical noise that's leaking out of the system. You can perturb a system sometime. We saw that work by Valeria this morning, and I'm going to go over that a couple slides. You can subject a system to some punishment, and usually the way it reacts can release some secret information. And then my favorite is a handful of cash. Attack the users, right? That's why when you go work for the government, they want to make sure you don't have a gambling addiction, right? Why? Because if you've got a gambling addiction, you're susceptible to that pile of cash for those secrets. And if you read the security literature, social hacking, as they call it, is a very powerful technique to infiltrating a system. There's a classic example where there was a company that was hired to penetrate a company, and all they did was buy one of their cordless handsets. They sat outside the business and listened to what was going on, all the conversations in the building. They learned that there was a new assistant to the CIO coming in, starting work in 2 weeks. They arrived a week early, saying they were that person, and basically pulled all the information out of the company. So that's another side channel, the people. So here's an example of a side channel attack that was performed on DES, the old encryption standard. What it does is you take a system that's running DES, and if you're a user on that system, you continually invalidate the cache of the system. What is the cache? The cache is a piece of memory close to the processor that holds memory for fast access. Now, in the case of where you always know where memory goes in this cache. So let's say that your algorithm, like DES, when there's 1 bit in the key, goes this direction. When there's a 0 bit in the key, goes this direction. Well, now what you can do is, as another process, you can figure out where in the cache would the 0 code be. and constantly invalidate it. Put your own stuff there. So that the speed of the algorithm is a function of how many zeros there are, because it's missing on that code all the time. It's running very slow. Now you reveal information about how long it takes the code to run because you're manipulating its cache and changing its timing. Many published attacks on DES. Now AES is much smarter. AES, there is no branch, there's no change of direction in the program that's a function of the key. That is part of the design. So you can change the key all you want. It takes the same exact number of cycles to execute in terms of fetching the code. And that gets around this attack. Yes?
Wasn't there a cache-based attack on AES?
And that's in the next slide. Thank you very much. It's in 2 slides. There is. It's in the data cache. It wasn't in the instruction cache. Yes?
To clarify that, that's not the mathematical algorithm of the operations they're doing, that's the implementation is the one to be.
Yes. So the thing about DES is when there's a 0 in the key, it goes and executes this code over here. When there's a 1 in it, it goes and executes this code over here. So what we do in this attack is we make sure this code over here is never in the cache. So if you have a lot of zeros in your key, it takes a long time to run because you're constantly missing, having to pull out of DRAM into your cache. And so now we know how many zeros roughly you have in your key. And imagine if I say, you've got to search 2 to the 128 keys. If I come to you and say, oh, by the way, there's 16 zeros, that will save you a ton of time. Right? It takes it from infinite amount of time, essentially, to 2 minutes.
And you don't have to measure over the entire calculation?
No, you just have to, pick all the values that have roughly that number of zeros.
Half the calculation, so this
Exactly. Exactly. Yes?
So instruction counters hacks like this, is that the same as time-based attacks? Are they analogous or are they different?
Usually time-based attacks are, they're network-facing. So a classic time-based attack is on the old implementations of RSA where it would invoke a function for every 1 in your key. So then what you would do is you would go and you would ask it to encrypt different things, and the amount of time it took to return that result was essentially information about the number of 1s. So time-based attacks usually don't have access to the system, and they can't manipulate the underlying microarchitecture, whereas cache-based attacks is a timing-based attack, but it's manipulating the system. So that's the distinction. All right. So now this one blows my mind when I first saw them doing this. This is a system where there's an unknown secret key on the system. They're able to send the inputs into it. They're going to measure how much current the system draws. And with no knowledge of the underlying implementation, they're going to figure out what the key is. Very clever. It's called differential power analysis. And it's differential because they have the system and then they have a model of the system. They know that, for example, multiplies take more energy than adds. XORs take less energy than adds. If you know the algorithm and you know what it should be doing and what type of operations it's doing, knowing the amount of current it draws and how that current changes when you change the inputs yields information about what the key is. What were the adds? What were the XORs? What were the multiplies? And so that's the differential analysis. So we're going to take some key that we don't know. We're going to inject in plain text into this system, and then we're going to essentially use estimation. We're going to look at a particular sequence of operations. We're going to estimate the amount of power it takes. What that will do is, for example, in AES, it's almost all XORs. So if we can identify a particular operation's power draw, we know how many in the key in the plain text, how many pairs were 1 and 1, how many were 0 and 1 or 1 and 0, and how many were 0 and 0. And that takes that key search and massively condenses it because we have so many properties about that underlying key information. It can make it quite easy to attack this system. So AES has been power attacked quite a bit. The way you get around power attacks is you have to make sure every operation takes the same amount of energy. So you'll usually find that encryption engines, they use really inefficient hardware that draws a lot of power for everything. So it's hard to do these attacks. This is Bernstein's timing-based attack, which was done on AES. And now we're going to kind of dive into the math again real quick. This is the ungentle part of the talk. So this is a really brilliant attack. What he did was he came up with a way by timing the AES encryption. He doesn't know the key. He's changing the plain text. By timing the amount of time it takes to the cycle, he infers what the key is. And I'll just show you how this works. And this kind of illustrates how a differential attack works. Differential attacks what they try to do is they try to listen in this world of operations, billions of operations. They try to listen to one operation, one. And they try to measure how much time it takes or how much power it draws, ignoring the other billions of operations. And how it does that is very clever. So the way Bernstein did this is he tries to listen to one single XOR in an operation that takes millions of cycles. And it's that XOR right there. That XOR is going to take key 0, the 8 bits, least significant bits of the key, and XOR it with the 8 least significant bits of the plain text. So he's going to listen to that XOR. Now, where the plain text and where the key is located is going to determine how fast the access is in the cache. Now, then what he's going to do is he's going to look at, when I change my plain text, how does it vary the amount of time it takes to do this one single operation? But how can he do that in the presence of billions of other operations changing? Let's look at the basic algorithm. So he's going to watch the time taken by the victim, the machine that he's injecting plain text into, to handle many random different plain text values. So all he's doing, he's changing all the plain text except that one initial byte. By doing that, he's randomizing all the other information that's happening in the system, and he's left with just that one operation's latency, how long that single operation takes. Now doing that, let's say he says, for example, when he looks at the 13th byte of the plain text, he notices that the longest execution happens when that value is 147. And so what he does is as he changes that input on the plain text, he listens for any spikes in the amount of time it takes to execute that single operation. Then what he does, on the same exact machine, he goes and he fixes the plain text, and on his own machine, he varies the key, leaving the plain text fixed. As he varies the key, he looks to see, for what key value do I get the maximum latency? If he knows the maximum latency is for a particular key value of this, and he knows that XOR is 8, he can then work backwards and know that when 8 XORed, when this value XORed with this value, that's the maximum latency, that's the key byte. So what he does is he looks at, when I inject different plain text, which value gives me the maximum latency. Then I turn around the algorithm. Because of the symmetry of XOR, I inject different keys, leaving the plain text the same, see where I get the maximum. Now I have both sides of this equation, and I work back and I can figure out what the original value was in the original attack.
So where's the variation of the time? I mean, it's a constant time to do an exclusive OR.
Yeah, the variation comes in how much latency it takes to access the data out of the cache. If all of your access latency is the same, you don't get any information out. So what Bernstein's hoping for is that there's some interactions in the cache with other key data, with other plaintext data, that just knocks this one access out and makes it longer latency. So I can identify this one access. The way to protect against this is to not use a cache. So you'll see super secure systems will not use a cache. All right. So I'm going to skip ahead here because I only got 10 minutes left. But this morning you saw Valeria talked about the fault-based attack. I won't go into that again because I got to reclaim a little time here. But basically this is an RSA-based attack where she took a system, she took a system and by manipulating its voltage, she injected faults into the system, and every time a fault occurred in the system, she was able to get 4 bits of key out of the system. She talked about that in her talk this morning. It took about 100 hours to attack that system. Extracted the entire RSA key. All right, so part 3, there's a bibliography for it. And now let's take a look at some tools that are open source tools that are really useful today for building more secure software. Probably the most popular one is Valgrind. Valgrind. Okay. I'm going to say Valgrind, but yeah, Valgrind. Okay. Do I have to roll my R? Okay. Valgrind. Valgrind is a platform for implementing analysis of software. So there's a variety of tools built on this. But some of the really good ones are Memcheck. This is a tool that finds buffer overflows, that classic buffer overflow. Hellgrind finds race bugs. Basically what it is a virtual machine. It's a virtual machine for x86 on an x86 machine and translates your code to a version of the code that adds checks to all of your operations to see if there's buffer overflows, to see if there's race bugs. And it's actually a platform, so there's many different tools. There's a tool called TaintCheck built on top of this that does taint analysis. And very, very powerful analysis. The main downside is you take probably 5 to 50x slowdown in your program. But it generates a lot of very valuable information that can help you fix bugs in advance of releasing your code. So definitely one to take a look at, a very mature piece of code, a very powerful tool, and open source. And you can build your own analyses on top of it. Now here's one for the BSD crowd. OpenBSD implements stack canaries using a tool called ProPolice that was developed by IBM. And it's a little bit more advanced than the canaries we looked at earlier. So they do put their arrays in front of their canaries so that we have to go past the canary to get to the return addresses. It also puts any pointers in the stack frame in front of the arrays, because when you're going to overwrite an array, you're going to go in this direction. And that makes it impossible to overwrite any code pointers that are in the array, the local frame. And examples of code pointers in the local frame are any virtual functions in C++. So if you have the ability to overwrite those, you can change, basically, the attacker can do polymorphism on your variables without your knowledge and change what the implementing methods are in your class structure. But by putting the pointers in front of the arrays, you can only write this way. Very powerful tool. And this is why OpenBSD is really such a hardened platform, such a great secure platform, because it uses a lot, this as well as many, many other technologies to harden it. Another thing you can do to really harden your program against these bug-based attacks is to do better testing. And so I'm sure we all write our tests before we write our code. But if we don't, a great kind of tool to use is a fuzz tester. A fuzz tester is essentially a tool which can generate random inputs for your code. What's so great about a fuzz tester is it doesn't have a preconceived notion of what a correct set of inputs should be. It's just generating random inputs. So it's very powerful at exposing what are called the shallow bugs. Those are the bugs that don't require a lot of different conditions. They don't require very deep sequences of branches to get to the particular bug. All they require is that, there's no preconceived notions in the input. And they're very powerful. A great one to take a look at is CrossFuzz, which is Google's web browser tester. It's a tool that generates a random web page with random JavaScript and gives it to the browser. They found hundreds of bugs across every web browser using this tool. That single tool has raised the quality of browsing and killed a lot of zero-day exploits in the world today. Very powerful tool. And it gets this power because it doesn't have any preconceived notion of what a correct page is. Now, if you want to get deeper bugs, you need a more powerful fuzzing tool. And a great one to take a look at is Klee. There's a commercial version, non-open source, sold by a company called Coverity, if you've heard of them. But essentially what this tool does is it looks for deeper bugs by taking fuzzed inputs, so it's generating fuzzed inputs, and then looking what's your code coverage. As it continues to generate fuzz, it'll track where am I executing, what are the paths through the code, and it'll say, why don't you execute this path? You never go this direction, then this direction, and then that direction on a branch. And then what it does, when it finds one of those places where you don't execute, it uses a theorem prover to try and figure out how do I change the inputs to go a different direction on this branch. And that's why it can find the deep bugs. It can find, what's a deep bug? A deep bug is I need this condition on my inputs and these three options set in this strange manner, which gets me down this really bizarre sequence of code and then hits a bug. And the way it gets to those deep bugs is through theorem proving techniques. So on the upside, it gets very deep. On the downside, the process of finding the inputs to go that different direction on a bug could take 16 hours of computation. So they use GPUs, they use multiprocessors, a very computationally laden process, but extremely powerful. Klee found hundreds of bugs in the GNU bin utils, including bin utils that have been stable for years. So very powerful tool. Very powerful. Now another great tool to use is Metasploit. Metasploit is a tool which packages up attacks. And with a press of a button, will attack a machine on your command. Now this is a different approach. This is asking the question, the previous tools asked the questions, do I have bugs in my code that can lead me to exploitation? This asks another question. It says, am I exposed to known exploits? The kind of exploits that people run with Metasploit. So this tool can when you go to the website, it says the tool is used for penetration testing. They want to see, is it possible to penetrate your machine with these known exploits? But it's a very controversial tool because it contains a number of facilities that would only be useful to an attacker. Like for example, it'll package up a rootkit in your penetration test. Now why would you want to put a rootkit on a machine that you're pen testing? Wouldn't you want to just know that you can get in, or do you want to put something there?
I think last week, and I probably did this previously as well, they released a new social engineering test as well, which is fantastic. It makes it dead easy to send somebody an email with a graphic or a JPEG or something in there to basically to penetrate the host. So yeah, there's a lot of interesting to it.
Yeah. Yes.
It's very useful to exercise a vulnerability that you detect, a potential vulnerability. You want to exercise it to confirm that it's really there.
Yeah.
Metasploit going one step further is a bit like fishbee.com, where you provide your own users' email addresses and it sends different phishing messages to them and then tells you which of your users responded to the message. So sometimes you actually have to commit a genuine exploit. all good.
Yes. Okay.
The colour of the inside can be slightly different from the outside.
Yeah. So the takeaway here is that using tools that understand these exploits can give you a lot of confidence that your system isn't vulnerable to them. Now, these are only going to cover the known exploits. Then there's the unknown exploits as well, which is, to get rid of those, you really want to get rid of the bugs. And then a similar tool would be like Nmap. Nmap's a tool that will take a forward-facing machine, one of your machines that's on the network that is publicly accessible, and will essentially enumerate all the attack vectors on that machine. It will look at what ports are open, what are the applications running behind those ports, what are the versions of those applications, and are there exploits in those forward-facing access points on your machine. So again, penetration testing. With knowledge of known exploits, is this system easily taken over? Does it have versions of stuff that are a problem? A very popular and powerful tool. So there's an example of tools to find bugs, tools to test better, and then tools to take known existing exploits and known versions of code that are exploitable and identify if those are in your system at some time. So lots of different tools you can use to help harden your system. If you want to learn more, my wiki page is currently empty, but I'm going to go put these slides on it as well as pointers to all of these code. I'll do that tonight. And I'm also going to put my 5-day version of this course up as well. So if you're interested in this material, I've got 5 times as much stuff there. So you can take a look at it. And great reading is the USIC Security Conference. Always fun to see what's happening there. Last year, there was a paper about a bunch of researchers that were able to drive next to a car and turn it off through the Bluetooth. It's just amazing hack. And the IEEE Symposium on Security and Privacy, the Cryptography Conference, Wikipedia is exceptionally good in the area of security. So it's a great resource. Not too useful today, actually, but tomorrow it should be back to normal. Slash.security is a great source of news. Security Now podcast is a great place to learn about news. Schneier on security, great blog to read for the latest news. So definitely check that out. All right, that's it. That's all I got.
Has anybody got any questions for Todd?
Yes.
Just a comment more than a question. I had a bit of a field with Metasploit and Nmap a while ago, and there's a very trivial combination of those two called AutoPorn. It just does a...
It's called Wormhole?
AutoPorn. AutoPorn. It's got like a SQL backend, so we'll do an Nmap of a subnet.
AutoPwn.
Yep. It'll do an Nmap
Okay.
and detect the vectors.
I see.
And squirt them in with Metasploit, and it's all completely automated. You just set it, and there are live distributions that you can boot off on a machine and just hit go, and it'll just own whatever you can.
That's a great point. So let's say you want to do pen testing. Do you install all these tools and then, there are Linux distributions out there which are pen testing distributions that put all this stuff together and give you a UI when the system boots up, and basically you point it at a machine and it starts attacking. For good or bad.
You point it at the network. You just put it, plug it into the network.
And it discovers what's out there. Yeah.
Don't have coffee.
Yeah. It comes back with a report. Yeah.
I just wanted to, regarding the taint checking or the user input that doesn't get validated, there was a good talk in the Open Programming Miniconf about a static code analysis tool for PHP called RIPS, or PHP Scanner.
Yep.
And the guy who talked about it downloaded a bunch of PHP programs from Freshmeat and just ran it over them to see what kind of results he got, and there just was like so many things where user input was not being validated at all. It was quite scary, actually.
Yeah, that's so I didn't talk about any of these tools, but static analysis tools are very powerful tools. Essentially what they do is they don't presuppose what you will run. They essentially discover paths that can go through the program and look for bugs on those paths. And like fuzz testing, because they don't put presuppositions about what are valid inputs, they're really effective at finding holes in your program. And in fact, when you look at the bugs these tools find, typically they'll find exploits on error handling paths. Because imagine you're writing your code, you concentrate on, this is the thing I need to do when it's working right. Oh, when it's wrong, I'll just close the file handle and do or whatever. Or you forget to do the close the file handle. Now there's a dangling pointer in the system that you can attack. They're very, very thorough, very effective tools. Their main downside is they can't go super deep into the code. And by deep, I mean they can't go, I had this option followed by this option followed by this kind of header followed by this kind of attack, because it gets too computationally complex for them.
Okay, any more questions?
Thanks for your talk, it was great. Lots of the tools and whatnot that you've presented focus on people looking at computers as a whole and code running on an operating system. What about people that are focused more on the embedded side? Do you do much work in that area?
In the what?
Sorry, hold it closer. On the embedded side, security for heavily embedded code.
Yeah. Oh, well, great question. I just ran a panel at the Design Automation Conference last summer. It was on embedded security exploits. And so we had the person that took over the car. We had the person that took over the pacemaker. We had a person that took over a UAV. It was the scariest panel I ever saw in my life. And the takeaway is that in the embedded world, people, they're really behind the server world and the desktop world in terms of their sophistication on providing protections against security exploits. And so the hacking community is really moving quickly into that space and starting to look at attacking embedded devices. And that can be very scary because there's a lot of embedded devices that do things that are, you don't want them to fail. Like those pacemakers, like those cars.
Like those UAVs.
Like those UAVs, yeah.
Yeah, talking to that one, the big one, of course, is the SCADA stuff. We've got a reasonable size plant in our place, and I'm always amused to see, well, first that the guys who build the SCADA systems really aren't IT people at all. They're plumbers and mechanics, and even modern equipment that goes into SCADA systems, it's still 10 megabit half duplex. And like, why are all these network errors? And like, because you're using equipment that was built in 1999.
Historically, the SCADA networks tended to be closed networks as well, and increasingly they are on the public internet.
I encourage people to work in the area of security. If you find this interesting, pursue it. It's a really interesting area. And like, funeral homes and dentists, there's no end to the amount of work in this space. It really is an interesting area to work in. It's if you like the fiddly bits of systems, it's pretty approachable, and you don't have to be a bad guy. You can be a good guy and do a lot of work. A lot of institutions don't have security experts, and so there's plenty of work. Attack their system and get a job, right? That's what Geohot did.
Attack your system and get a new job.
Yes. All right, thank you very much.